This presentation examines the foundational paper titled Attention is All You Need, originally authored by Ashish Vaswani and collaborators from Google Brain and Google Research. Can modern sequence models operate efficiently without recurrence? We explore the transformer, a paradigm-shifting architecture that achieves superior performance and parallelization capabilities purely through attention mechanisms. Recurrent neural networks, specifically LSTMs and GRUs, have long defined the standard for sequence modeling tasks. However, the inherent sequential nature of these models poses significant barriers to efficient parallelization during training, especially with increasing sequence length. This presentation examines a paradigm shift in sequence transduction, the transformer architecture, which entirely discards recurrence. The transformer relies exclusively on attention mechanisms to draw global dependencies between input and output positions. By achieving constant path length, this model significantly enhances both computational speed and optimization capabilities. We will first explore the efficiency metrics that justify this architectural change, before detailing the core components of the multi-head attention mechanism. Recurrent neural networks, particularly LSTM and GRU variants, have long been established as the state-of-the-art approach for sequence modeling and transduction tasks. However, these models inherently factor computation sequentially along the input and output positions. This critical limitation precludes effective parallelization during training, which represents a significant computational bottleneck. As sequence lengths increase, memory constraints further compound the challenge of sequential computation efficiency. Furthermore, while attention mechanisms enhance dependency modeling, they are typically utilized in conjunction with the underlying recurrent framework. This fundamental constraint of sequential processing limits scaling and necessitates the exploration of new architectural paradigms, setting the stage for the architecture introduced in the following slides. Comparing different layer types requires evaluating efficiency metrics like per-layer complexity, minimum number of sequential operations, and maximum path length. Recurrent neural networks exhibit a linear dependence on sequence length DAO for both sequential operations O1 and maximum path length O1, hindering parallelization and the capture of long-range dependencies. Self-attention layers fundamentally overcome these limitations by achieving optimal O1 complexity for both sequential operations and the maximum path length. The constant path length means any two positions are connected in a single layer, significantly easing the optimization process for global dependencies. Although the standard self-attention complexity is O(n) squared times d, this cost is often justified by the massive gains in parallel computation and speed. Furthermore, convolutional layers, while parallel, still require O log of k times n path length, needing many layers to achieve global context. These combined advantages in path length and parallelism establish self-attention as the preferred primitive for sequence transduction tasks. The transformer model, designed for neural sequence transduction tasks, fundamentally departs from prior methods by completely eliminating recurrence and convolutions, addressing the path length limitations discussed previously. It adheres to the classic encoder-decoder structure, where the stacked encoder processes the input sequence on the left, and the decoder iteratively generates the output sequence on the right. This entire architecture is built solely upon layers utilizing multi-head attention and position-wise feed-forward networks. Within the encoder, representations are refined through self-attention, allowing every input position to attend to all others simultaneously. The decoder incorporates two attention sublayers, a mass self-attention mechanism to ensure autoregressive decoding, and an encoder-decoder attention layer that queries the encoder's output. Since recurrence is removed, positional encodings are critically added to the input and output embeddings to inject information about token order, a crucial concept we will examine shortly. The core mechanism of the transformer is the scaled dot product attention, illustrated in the figure's left panel. This process computes compatibility between queries and keys, scales the result by the inverse square root of the dimension, and applies a softmax function. This necessary scaling factor prevents the dot products from growing too large, which helps stabilize gradients during training. This fundamental building block is expanded into multi-head attention, as depicted on the right. This design allows the input queries, keys, and values to be projected into multiple distinct representation subspaces in parallel. The results from these parallel attention heads are concatenated and then linearly transformed to produce the module's final output. This parallel computation provides the model with the capacity to capture diverse and complex dependencies simultaneously. Following the multi-head attention mechanism, each encoder and decoder layer includes a position-wise feed-forward network. This component is crucial for introducing nonlinearity and further mixing the feature representations at each location. The network operates on each position separately, applying an identical, fully connected transformation across the entire sequence. Structurally, the module consists of two sequential linear transformations separated by a standard ReAU activation function. While the weights are consistent across all token positions within a given layer, they are explicitly reparameterized for every subsequent layer in the stack. This structure effectively enables the model to process local feature information independent of the attention output. The absence of recurrence and convolution in the transformer means the model possesses no intrinsic knowledge of the sequence order. To address this critical limitation, explicit information regarding the relative or absolute position of tokens must be injected into the system. This is achieved by adding positional encodings directly to the input embeddings before they enter the encoder and decoder stacks. The authors implement a fixed method, utilizing sine and cosine functions of different frequencies across the embedding dimensions. This sinusoidal formulation offers two key advantages. It potentially aids the model in learning relative positions, and critically, it allows the architecture to extrapolate effectively to sequence lengths beyond those encountered during the initial training phase. Having established the architectural components, the performance benefits of the transformer must now be quantified against existing state-of-the-art models in machine translation. Focusing on the WMT English to German task, the transformer big model achieves a BLEU score of 28.4. Significantly outperforming the best previously reported systems, including strong ensembles. Similarly, for the English to French task, the big model sets a new record with a BLEU score of 41.8. Crucially, this substantial improvement in translation quality is coupled with a reduction in computational requirements measured in flops. The transformer-based model alone surpasses all previously published models at only a fraction of their training cost. These metrics confirm the efficiency gains realized by replacing recurrence with pure multi-head attention. A comprehensive ablation study was performed to systematically evaluate the contributions of the transformer's core components. This table details the performance changes on the English to German development set when key hyperparameters are varied. The analysis confirms the necessity of multi-head attention. While a single head significantly reduces the BLEU score, excessive heads also cause performance degradation. Crucially, the data supports the general trend that deeper and wider models achieve superior results, highlighted by the final big model configuration. Additionally, the designed sinusoidal positional encoding system proves just as effective as using learned positional embeddings. These findings underscore the optimal balance required in dimension sizes and regularization to achieve state-of-the-art translation accuracy. The capacity for attention heads to capture complex linguistic phenomena is essential for the transformer's success. Visualizing the internal workings reveals that the self-attention mechanism spontaneously learns to resolve long-distance dependencies. This specific example, taken from layer 5 of the encoder, focuses on the attention weights originating from the verb making. Multiple distinct attention heads shown by different colors clearly attend across several intervening words. Crucially, they strongly link making to the predicate adjectives more and difficult, thereby completing the verbal phrase making more difficult. This ability to establish direct, non-local connections between tokens verifies the efficiency of the attention-based approach in modeling sentence structure. This specialized focus confirms that different attention heads learn specialized linguistic roles. Individual attention heads within the transformer architecture learn highly specialized, structured behaviors related to natural language syntax. This figure illustrates two distinct encoder self-attention heads from the same layer, demonstrating how the multi-head mechanism allocates different internal roles. The head visualized on the left, shown in red, focuses predominantly on local context, often attending to the token immediately following the current word, or maintaining identity links. Conversely, the green head on the right captures long-range structural relationships across the entire input sequence. For instance, this head strongly links the main subject, the law, to modifying elements later in the sentence, such as perfect and application. These distinct specializations confirm that attention implicitly learns to encode diverse syntactic roles, crucial for subsequent complex linguistic processing, including the resolution of anaphora.